Hello, Professor Jack Walker. This year at the PLSO conference, I wanted to follow up on a presentation from last year where we're comparing some drone products with the same quantities computed by terrestrial surveying. So in particular, we'll look at stockpile volumes and a contour map of a 25-acre site. Unfortunately, we can't be face-to-face this year. However, by doing a pre-recorded session, I was hoping I could capture some of the actual software that you typically can't demonstrate in a live presentation, so maybe that will be something that adds a little value. So for decades, the classic photogrammetry relied on the ability of the stereo operators to be able to see stereoscopically and extract data in 3D. So originally we started off with the anaglyphic glasses, the red and blue stereo glasses. We moved on to the analytical plotters. We had two of them at one time at Oregon Tech. And then we moved into the digital or soft copy photogrammetry. The issue, though, is that many people don't see a stereo at all, or they see it so poorly they can't extract quality data. When the drones, UAS or drones, became legal for commercial flights in 2016, this is a whole new technology where the image processing doesn't depend on an operator's ability to see in stereo. So that was a new world for me. So we were fortunate to acquire a commercial drone and began teaching the students the use of the drone and the new software. And we wanted to investigate some of the metric applications of drone imagery. So many of the products that we generate in surveying require a fairly high degree of accuracy. So we tend to use the term survey grade accuracy. So one of the questions then is, can we generate survey grade products from drone image? So photogrammetry, one of the challenges is vegetation obscuring the bare earth surface. So in the Coast Range, good luck with getting any kind of a bare earth surface model with photogrammetry. Well, there are algorithms that remove spikes in a digital surface model. So a lot of times the user can go in and you put polygons around areas of high vegetation like trees, brush, medium and grassy areas, and you classify the road surfaces and the buildings, and then the software adjusts these smoothing and filtering algorithms. However, there is a learning curve associated with that. And I guess we wanted to start off with, something simple. Can we just use out-of-the-box software and avoid some of the more complex issues that could come up? So maybe the low-hanging fruit for getting into surveying with a drone is stockpile volumes. Stockpiles tend to be bare earth surfaces. They're fairly new. You don't typically have heavy vegetation on them. So could we just use the stock settings and determine an accurate volume with a stockpile? We are working with some gravel stockpiles on Stuckel Mountain, and historically the equipment operators have always shaped the piles. And they're absolutely beautiful. These nice, perfectly tapered sides, flat top, nice rectangular shape. And the reason they did that was just for volume determination, to make it easy to get a length and width of the base, length and width of the top surface, and then the height of the pile. And so one of the questions is, do we still really have to do that in today's world? So Klamath County, the Public Works people were interested in using drones to determine the stockpile volumes. What would the methodology, the procedures and protocols look like? Also, kind of as an afterthought, they said, could you create an actual 3D model of the cliff face above the stockpiles? They're looking at some long-term renovation activities. The geomatics department, we always strive to involve students with state-of-the-art technology, if you would, the leading edge. We tend to stay away from the bleeding edge of advanced research. That's not really our mission. But we love to involve students in applied industry projects where they have some real deliverables for real people rather than a hypothetical type project. So I guess the question then, if the UAS or drones can determine accurate stockpile volumes, does the shape of the stockpile matter? Would it be possible for Klamath County to just push up the piles as most efficient and convenient and determine a volume without having to go through and shape them? Okay, so why don't we take a look at the Stuckel Mountain quarry site in the gravel stockpiles. So this is Hill Road, and then we go into the gravel stockpiles. They currently have 4 stockpiles here, and then here's the quarry face. From the lower, sometimes they have more gravel stockpiles down here, so they could actually have 6 or 8 of them. From the lower stockpile up to the top of the quarry face is about 550, 600 feet. So quite a bit of relief in the area. So let's take a look at a video made from the 3D surface model generated from the drone image. So you can see the ATV people just love to find these stockpiles and drive all over them, going up onto the quarry face. With video, if you make a real smooth video, the file size becomes prohibitively large. So I'm trying to find a good compromise between file size and smooth video. So this was the site, I believe about 60 acres overall. The gravel stockpiles are distributed over about a 20-acre site, doing this in 2 different flights. So for the stockpiles, we were looking at putting permanent pre-marks, ground control points that are marked, pre-marked, so they're visible in the imagery around the stockpiles. There's some existing large boulders. The county has pre-made concrete barriers that they could place around the stockpiles. Something that wouldn't have to be repeated. You could establish some GCPs and then just come back and maybe freshen the paint and use them. So placing the gravel stockpiles efficiently, don't worry about shaping them. Design automated drone flights. So one person could go to the site, just launch the drone, fly the predetermined pattern, go back in the office, and then have volumes computed in, well, maybe an hour is optimistic. Drone processing takes some time, but while it's processing, you can do other items, and then you can update the volumes without having to reshape the pile. Fairly efficient. And part of our learning curve was looking at the effect of using 2 different sensors. So we're fortunate to have a high-end commercial drone. It has Sony Alpha 7R camera. It has the higher quality Zeiss lens on it. It has a more expensive advanced CMOS sensor, really good dynamic ranges and all kinds of things. So getting some high quality imagery without going to the very expensive calibrated metric cameras. And then we also acquired a Parrot Anafi drone, which was about $700 as I recall. It's really optimized for high definition video. So it does have a Sony lens. It's a good lens, inexpensive compared to the Intel drone lens, optimized for video and not imagery. Notice that Parrot now has a Anafi USA model with no Chinese components. Might be something of interest. Okay, so the drone flight planning, the Parrot Anafi, it just uses your smartphone with an app on it. You pinch and size and move a polygon around. Doesn't always register well with the ground. I did a little project where I centered the rectangle on my project, and then the actual only flew about half of the project. So I had to stop, move the rectangle, and fly. I think it was about the third flight before I got it right. Don't have that problem with the Intel drone. You can only specify a constant flying height. So for steep terrain, it makes it really difficult. For the gravel stockpiles, we were flying quite low over some of them and then quite high over the other ones, so doesn't have a lot of control there. The Intel flight planning software, what they call their mission control software, has terrain following. So it will maintain a constant flying height above ground level over rugged areas using the coarse DEMs that are available worldwide. It controls the camera angles to be sure you have the proper overlap of the imagery, and gives you visual quality control information, and you can tweak things around until you have good ortho coverage, and you'll generate good stereo quality surface models. Know your airspace. The Stuckel Mountain Quarry is located within 5 miles of Kingsley Field, which is Class D airspace. So authorization is required to fly in classified airspace. You don't want to get yourself in trouble flying in an area where you lack the authorization. So a couple of options here. One is the new Lance system. Low altitude authorization and notification capability. You can go on the internet and select a grid cell, and you can make it an application to do a drone flight, and then hopefully in just a few minutes you can get approval. So let's go take a look at that here in a minute. The issue is that when I went to the Stuckel Mountain over the Lance grid, the drone flights were limited to 50 feet above ground level. So to cover 20 acres with a flying height of 50 feet AGL, it would require 6,500 images. I don't think the basic Pix4D software would even process that many. And if it did, the airbase, or the distance between exposure stations, is very short, and that can introduce some errors into your processing. So that wasn't a very desirable option for us. Option 2 is to contact the air traffic control. The tower controller was easy to work with, explained what we were doing and using visual observers and everything, and he was real easy to work with. So he authorized that we could fly up to 200 feet AGL. So for the 20 acres, for the 4 stockpiles, that reduced it from 6,500 images to 488, which is doable. The ground sample distance, or the grid spacing of your 3D points, is 3/100ths of a foot. Well, that generates basically 1,000 3D points per square foot. Incredible, maybe incredible overkill. However, we were limited then with the Intel drone, with that camera. It would have been preferable to fly at the maximum legal flying height of 400 feet and reduce it down to a mere 275 points per square foot, but we didn't have that option. So here is the Intel mission control software. This is our project area, and it shows us that we are within Class D airspace. And in the Lance grids, notice some of these grids you can fly up to 150 feet. Where we are located, unfortunately, is 50 feet. Even 150 wouldn't have been a very good solution. So the processing software, notice that it allows us to turn on and off the areas, controlled airspace, airports. You can go find, it's amazing how many little airports there are. The Skywagon Ranch, the Long Ranch, and so as a commercial operator you have to be careful there. Helipads, hospitals, parks, power plants, prisons, special use, TFRs, temporary restrictions, what have you, airports. So just to clean everything up, let's take a look at that, turn some of those off. We go into the Stuccal gravel stockpile area. This is the flight that covers the quarry face. So we can do some different things here. Let's see. The current flight plan, we can turn on and off the coverage, overview, takeoff position. So let's take a look at the, simplify some things here, turn off the waypoints. So this is the coverage, just turn it off. So here's the area of interest. So here was our cliff face that we're trying to cover. Flight path that'll do that. And of particular interest is the coverage preview, that if it's green, it means we have a good quality stereo overlap, if you would, or intersections, and we can generate what they call a true ortho, or we're going to get good XYZ positions. In the yellow areas, there's a little strip here that's yellow, then it's lesser quality, and the red areas are not good. So you can change your flight parameters until everything in your area of interest turns green. And let's take a look then. So in 3D, you can see how this is a terrain following flight, which is a tremendously appreciated capability. It turns out that this is about a 30-minute flight. The Intel drone has a flight time of about 12 minutes. We can start the flight, and after the battery's getting low, you pause the flight, land two batteries, so you can swap one of the depleted batteries for a fresh one, then the other one, go back up and just resume the flight. So you can do as many hot swaps as you need to complete a flight. And of course, then you're kind of just limited by line of sight, the having to keep the drone within line of sight. So this was the quarry area. This was what, 884 images, and then we had a separate flight down over the gravel stockpiles, and then both flights, all the data was put into Pix4D and processed simultaneously. This is the flight over the gravel stockpiles, which is, and you can see again, it's the terrain following flight. And this one was, I think, one flight. I think we were able to get it done in about 15 minutes, one flight. Okay, so just a quick summary. We were authorized a 200-foot AGL. Terrain following was greatly appreciated with a steep hillside like that. So we actually flew at 60 meters, 196 feet, and it worked really, really well. So flight one, 24 acres, 488 images, about 150-foot elevation change, 15, 16-minute flight. And then flight two, the quarry face, 60 acres, 880 images, 350-foot elevation change, about 37 minutes with hot swapping there of the batteries. Ground control points. So Pix4D recommends 5 to 8, However, for those of us that are interested in accurate metric results, would highly encourage you to use more than that. So we established 20 ground control points and set pre-marks on them. We used 3 of them as checkpoints. So they were not used in processing the imagery, and when everything was processed and was completed, then the computed positions are displayed next to the known position to give you some independent quality control. So always plan on using a few checkpoints. Okay, so the imagery was processed simultaneously, 1,368 images. Took about 11 hours to process all the way through the 3D model. So basically, to me, that's overnight. You set it up and hit the process button. We come back the next day and it's done. Oftentimes, I wound up processing the drone imagery several times. Maybe you have a GCP with a high residual and you go back and look at some of the images and you didn't get a real good pointing on some of them. There is an automatic pointing routine that sometimes it doesn't do a good job, and so you touch up some of your GCP observations, wind up adjusting the DSM filtering and smoothing algorithm. What I found is when you do contours, the way they cross a hard surface, a paved road, is not correct. If you go through and you make a polygon over the road surface and you tell the software this is a road surface, then it does a really good job. Of contouring the road surface. We didn't really want to start off with having to do a lot of this advanced image processing settings, not having much experience with it. So the stockpiles used the default Pix4D settings, processed the data, and it came out really well. So trying to keep it simple as we enter the learning. Here are some photos of the Stuckel gravel stockpile project. Beautiful day in October. Brought along Subway sandwiches and soda and water, and we really had a nice day. It was a Saturday. So here's one of the gravel stockpiles. Here's the quarry face behind the stockpiles, one of the students with the reflectorless total station, and Professor Marker setting up our Faro scanner, graciously donated by Faro. Interesting to note, the scanner and the reflectorless total station, you couldn't capture any points on top of the stockpile. So this was the southwest stockpile where we were comparing the drone and the 2 terrestrial instruments. So we went up to the terrace above, which has 2 more stockpiles on it, to look down and capture the top of the stockpile. The Faro scanner wouldn't look down steep enough to capture points. So we used the reflectorless total station to get points on top of the stockpile. Stockpile is pretty much flat on top, so didn't need a lot of points to get an accurate surface model for the top of the stockpile. Okay, the students rotated through operating the instruments, and I think they learned quite a little bit there. And here's something that I've come to enjoy very much is the biodegradable pre-mark. We typically would set a hub and put a tack there with the pre-mark and then position it, put a couple of just iron nails in to keep the wind from blowing it, and then you don't have to come back and pick them up. Within a couple of weeks, the colors have faded and the cardboard just biodegrades. Very useful. In some of the areas where there was quite a distance between the ground control points, maybe some steep changes at the bottom or top of a cliff face, I put in some manual tie points that were just painted on boulders. Brought along a generator, so trying to charge batteries as we flew and worked, and keep enough batteries to get everything done. We had some winds gusting up to 15-20 miles an hour, and with the quarry face creating some pretty strong up and down drafts, but the Intel drone handled it very well. The Falcon 8 drone with the Zeiss lens The lens then will calibrate a little better, give you better metric results with a better lens. Another picture of the Falcon drone, the cockpit for the drone, and then flying the drone. So had a good day. Always nice to involve the students in a real project. Let's review some of the basics of photogrammetry here. It will allow us to experiment with simplifying some of the procedures for determining or possibly determining the volumes of the gravel stockpiles. So if you recall, if you have a pair of overlapping images and you want to create a 3D model from the overlapping imagery, we have to complete the interior orientation, which relates the image coordinates to the lens, and then we have to remove lens distortions. And once we have the interior orientation done, then we have to do the exterior orientation. Exterior orientation has two components. The first component is to scale the model. You have an arbitrary 3D model here with the same horizontal and vertical scales, but the scale is not the same scale as in a reference system or datum. With just a pair of overlapping images, if you have 2 points with horizontal positions only, no heights or elevations, then using the distance between them, basically, we can scale the model into our reference system. So once the model is scaled, then we have to level it. So we have a 3D model, the horizontal vertical scales are correct, but it is tilted with respect to our reference system or datum. So we need a minimum of 3 points, and just elevations only, no horizontal positions, 3 points with heights or elevations, and I can level it into my reference system. So those two steps determine the exterior orientation. If you want to determine an accurate volume of a gravel stockpile, if you're not interested in the location of the gravel stockpile, you're not interested in heights of or elevations of points on the stockpile, do we really need to go out and set GCPs and then use our RTN or RTK or total stations to put 3D positions on the ground control points? Or could we just set points and then measure the distances and use those distances to scale the model and get an accurate volume? So that's one of the things we will investigate here with our Stuckel gravel stockpiles. So this is the 3D model then created of the Stuckel quarry site. The gravel stockpiles, 4 of them currently, sometimes they'll have more. We can take a look at the idea for pre-marks. We put right around, this is the southwest stockpile. And we use them as ground control points, process the data separately, just using no GCPs, but just putting in those 4 points and putting in the known distance as what they call a scale constraint, and then we'll compare volumes and see again if we can get an accurate volume from scale constraints with no 3D GCPs. So as you can see, it's a futile attempt to keep the ATVs at bay. They've been putting in large boulders. Our thinking is, could you just put a boulder at the 4 corners of the gravel piles, set a PK nail, paint a pre-mark on it, then record the distance between the pre-marks, fly an automated drone flight, process the data, just measuring the pre-marks and putting in a distance. Could you get an accurate volume? If so, Klamath County has something like 15 or 20 stockpile sites, multiple stockpiles at some of those sites. And if you could have some permanent, not easily destroyed or moved pre-marks, that might make the process quicker and simpler. Notice that just this stockpile, which is about 170 feet long, 70, 75 feet wide, has almost 5 million 3D sample points in the point cloud. So in the surface model, from the drone imagery, you can actually see all these footprints. You can see the donuts that some ATV rider was having fun making. Pretty astounding level of detail from the drone imagery.
Let's look at the processed data. So the Falcon 8 drone, using the ground control points to process the imagery, create the surface models, draw a polygon around the gravel stockpile. Pix4D generates the volume and an error estimate. I'm always a little bit suspicious of software error estimates. It's fairly complex computations. Small changes in the assumptions you make can have a large difference in the computed errors. So as just a quick way to try to get a validation on Pix4D's error estimate, I made 3 independent polygons, 3 independent volumes and error estimates, took the mean and computed then the standard error of the mean, which wanted to compare with the Pix4D error estimates, and it looks really good. Now a sample size of 3 is so small that the mean error estimates, it bounces around quite a bit. This one's quite a bit lower than Pix4D. This one's a little bit higher, but in general it validated the Pix4D error estimates, and the Pix4D error estimates were very consistent from stockpile to stockpile. So a 6,000 cubic yard stockpile, 31 cubic yards of error estimate, 2,000 cubic yard stockpile, 13 cubic yards. So that tracks well. Kind of interesting just to look at the percent errors. When you generate the volume, is a percent error of that volume given the error estimate. So all of them basically came in at less than 1% with the Falcon UAS or drone. So 0.8%, 6%, 0.6%, 7/10, 4/10, 5/10, 5/10, 6/10, 6/10. So that all looked pretty good. So then the 2 stockpiles, the southwest and northwest, which are on the same terrace, we flew those with the Anafi drone. It doesn't have the ability to do terrain following, so we would have had to make separate flight for each of the terraces. We only got one of them done with time and battery constraints. So notice the Anafi drone, the error percent was 1.4 very consistently. I think we're seeing a difference in the quality of the sensor. The Falcon drone has the $3,000 Sony camera with the Zeiss lens. This is a much less expensive camera. It's a Sony camera. This is a $700 drone. If you can get a 1.4% error in a stockpile volume, that's not necessarily bad. Okay, so that gives us then a number of comparison points. So let's take a look at a summary here. For the southwest stockpile, where we had the terrestrial laser scanner, we had the Falcon 8 processed with ground control points, Falcon 8 imagery processed with no ground control points and scale constraints. So remember, the scale constraint is we had four hubs basically around the gravel stockpile. We just put in the 4 distances as the scale constraint to scale the model. To generate volumes, we used the Anafi drone for this one with ground control points, and then a reflectorless total station. I use the baseline as the terrestrial laser scanner, and we can see then the Falcon 8 with ground control points, with scale constraints, Anafi with ground control points, and the reflectorless total station. Percent errors, 0.5%, 0.2%, 0.6, 1.8. The reflectorless total station, a setup for each side of the stockpile, and then we had to go up on the terrace above the stockpile to see the top. So at each setup, a different student operated the instrument to get experience using the equipment and keep everybody involved. So one of the setups, for some reason, they didn't collect, I don't think, enough points on one side of the stockpile. The tin model has a couple of artificial little gullies or ravines in it. So I think that this 1.8% isn't bad, but I think it would have been a little closer if we had a few more data points collected on one side of that stockpile. So I would say any of these instruments would give you an accurate usable volume for a gravel stockpile. Moving on to the northwest stockpile, where we have again the Falcon with GCPs, Falcon with scale constraints, a NAFI, and percent errors here 1.3, 1.2, 50 cubic yards of error compared to almost 4,000. That's really, I think, very acceptable. The northwest stockpile with the Falcon as the baseline, Falcon with the scale constraints, another 50 cubic yards, 2.4%, and the southeast stockpile with the Falcon baseline, 50 cubic yards, 0.8% for that stockpile. So I was pleased with this data in the sense that I think it validates that the drone is a reliable instrument that we could use for generating bare earth surface models. So whether we want volumes or contours or got bare earth terrain, no vegetation, it looks like the drone is another tool we can put in our toolbox.
Here's another volume comparison project that we completed. On campus, they were putting up a small building, and they had brought in some gravel to use for the pad for the building. So it was convenient, and we decided to use this as a class project. So we set 4 hubs around the stockpiles, RTN, GNSS positions, process the imagery with the GCPs, and then that was a big class in the remote sensing, 20 students. So each student went in and they digitized and computed the volume of the small pile, the large pile, and then they did the exterior of both piles together, and then made a comparison to see how the sum of the small and large pile volumes compared with the composite total volume. So I had 20 students do that, and I did it. So I have a spreadsheet somewhere, which I can't lay my hands on right now. And again, the fluctuation in volume from the 21 independent tests was literally 1 or 2%. So it really worked well. To follow up on that, we processed the imagery again with no GCPs. And we just put in these 4 distances as what Pix4D calls scale constraints. Did the volumes of the small pile, large pile, the composite, compared those for consistency, which again was about the same, and there was no significant difference between the volumes, whether we used GCPs or scale constraints. So the scale constraint seems to be a viable method. Okay, here's another little test that I made using scale constraints and volumes. We put it in a new parking lot here on campus, and they had some trenches that they had dug here for the utilities. And I got the idea that the fill material and the cut material for these trenches should be pretty much the same, and also wanted to experiment again with scale constraints. So I went out just by myself and took a cloth tape, measured the distance between two expansion joints. I used a rock to hold one end of the tape in place. So I measured then 1, 2, and then from an expansion joint down to the edge of the sidewalk and the asphalt, and then to the other edge of the asphalt. So 4 scale constraints. So it didn't take me long at all. Just one person. I went out here and measured those scale constraints. And I digitized a couple of volumes so we can see this is kind of a topsoil material for this fill and cut here. And some of this lighter material is a deeper material that is left over from cutting the parking lot. So I tried to run my volume polygons where it didn't include underlying fill material. So I went in and generated volumes for what I called the East Trench and the West Trench. And I was really surprised at how close the cut and fill volumes came out. For the West Trench, 54.3 cubic feet of cut, 54.6 cubic feet of fill, difference of 3/10 of a cubic foot. The East Trench, 53.98 cubic feet for cut, 53.21 for fill, a difference of 0.78. So I think that is one of the takeaways, that if you want an accurate volume, that you don't necessarily have to pull out your GNSS receivers or total station, establish 3D GCPs, that you might be able to just go to a site quickly and easily, put out some scale constraints, obtain imagery in minutes, and obtain accurate volumes. So another tool in our toolkit there. Let's take a look at contour maps. So this was the very first drone project that I did. It was all new and I was just experimenting. Just north of campus is a 25-acre site, and one of our senior project student groups, they wanted to get some experience with GNSS RTK surveying, so they surveyed the site with a 25-foot grid and some break lines. So we already had their 1-foot contour map of the site. Could we reproduce it with drone imagery? So let's take a look at Pix4D. This is the site then just north of the campus here. And a few things to note. One, over in this area is a small little gully. It's only about a meter wide and about a meter in depth, so it's a pretty narrow, deep feature, which we'll come back and see how that processed. There's a small rock outcrop here. It's almost completely buried in vegetation. All this vegetation, there's just a few areas where the rock outcrop is visible. There is an old road here running through here with a uniform side slope or the cut slope. We'll take a look at that also. Small stream here. So the students ran a brake line in the stream and used the brake line when doing the contour processing, which Pix4D software module has no provision for brake lines. So let's take a look at how some of this, the ground surface is pretty uniform, pretty smooth. Brush, some scattered juniper grass here. About 60% of the area was matted grass. This was in the spring, so the snow and pretty well matted the vegetation down. Most of the leaves were gone, but there isn't a lot of texture. So it's kind of a soft, blurry surface. I wasn't real sure Pix4D would be able to match the location of one pixel on an image with the same pixel location on a different image. A little dubious about that. About a quarter of the area was heavy grass, almost waist high, and not much of the ground surface was visible. You can see a little bit of bare ground here and there. I wasn't real optimistic about that. It was only about 15% of the area where at least 50% of the bare ground was visible, and then the vegetation was very sparse and low. Pretty confident that the software would produce a good surface model here, not so much the other areas. A couple of areas where there was some tire ruts. Someone had driven through there in a muddy spring, and the tire ruts were 6 inches to a foot deep. However, the vegetation was virtually level. So the vegetation in the tire ruts was just a little bit taller, but the top of the vegetation was virtually the same and fairly heavy. I wasn't convinced we'd even see those tire ruts in the surface model created from the drone imagery. So here is the topographic contour map, 1 foot contour interval that the students produced from the GNSS RTK, so we can see. So zooming in, here's that gully. So the students captured points in the gully, and not sure if they put a break line per se or not, but it was captured correctly. Here's the rock outcrop. They did kind of just a rough outline of the rock outcrop, but it was preserved. Then the stream does have a break line in it. So you can see the contours pretty well V into the stream appropriately. The cut bank, the contours should be parallel running along this uniform cut bank, and they're not, but again, with a 25-foot grid, you're not sampling it very well. In processing the drone imagery, I noticed several things. Where the contours crossed a paved road surface, they didn't look correct at all. Some of the vehicles showed up in the surface model, which is something that you don't want. So I went in and classified the road surfaces and told Pix4D what they were. I told Pix4D that some of the vehicles were man-made objects and that they would be then removed from the surface model. So here is the surface model before any smoothing or filtering has taken place with the classified objects. I was really surprised at the detail. I guess we shouldn't be surprised. We generated 31 million points. There was 278 points per square foot. So let's look at that in Pix4D here. The surface model in Pix4D captured that gully in incredible detail. The rock outcrop was pretty much, again, just merged in with the vegetation. This is my vehicle, and I neglected to classify it as a man-made object, so we'll see that it shows up in the contour map. The gully was captured in incredible detail. However, Pix4D has no provision for break lines, so the contours don't necessarily cross the stream. The cut slope on the old road bank was, of course, modeled. So let's take a look and see how that showed up on the surface models. The digital terrain model, I just used the default settings in Pix4D, which is sharp smoothing and filtering, and notice the vehicles that I had classified as man-made objects were removed. Here's my vehicle that I forgot to classify. Looking at the contour map produced from the drone imagery, a couple things become apparent. The gully was over smooth. So we really needed some provision to come in and either run a brake line in it. I could have put a poly line around it and classified it as something to be retained in the surface model. After classifying the road, notice how the contours cross the road appropriately. They look pretty good. Here is the brake line transferred over from the student's data set, and you can see Pix4D contours cross the stream. It's a very gentle little stream, not very much of a sharp gully to it. So the contours don't look quite right. This one is Ving off the brake line. The rock outcrop was completely smooth. It was, since it was nearly buried in vegetation, that it was completely removed. Here's my vehicle with a bunch of little contour lines running across it. Where the drone imagery really looked good, this is that cut bank side slope, and with 278 samples per square foot, the contours really... So here's the composite contour map. The blue contours are from the GNSS RTK, the red are derived from the drone imagery. So overall, I was really impressed with the agreement. As we zoom in here and scroll and pan, I didn't find any area where the contours were crossing each other from the drone compared to the RTK. We did, of course, find where there was some issues with the rock outcrop being removed. The gully was over smooth. I neglected to classify one vehicle here. Overall, though, I was really stunned, even in the areas where there was the heaviest vegetation. The contour lines almost fall on top of each other. I don't think you could ask for a better agreement from drone imagery to the terrestrial GNSS contours. So one of the things that I'm currently working with is using software packages. We have the Carlson, what they call Precision 3D Topo, that will load these 31 million point cloud, and then you can thin them and simplify them, and then you can make it a small enough file that it will load into AutoCAD. So working with that, working with another software package called Global Mapper. We really need to be able to come in with the drone imagery and run a brake line down the streams, and do some editing here. So working on that currently. I'm currently working with the Civil Engineering Department on a senior design project. They wanted a surface model of this area west of the Oregon Tech campus. So here's the campus boundary road, Dan O'Brien Way, about 60 acres. So I flew a little lower, obtained 700 images, I believe, and currently processing the data. And I'm using another software package to take the basic output from Pix4D and process. The software package is called Global Mapper. So looks like it has some very useful features here. So one of the things that you'll notice, this Dan O'Brien Way is along this curve is super elevated. So unless I went through and classified that road surface, the contours didn't cross the road correctly. And then once it was classified, they looked very, very good. This is a downslope coming into a sag point, low point, and then climbing back up. The road also has a crown to it. So you can see how the contours are coming in at the sag point, but they don't quite reach the crown height. And the contours are reflecting the surface slope and the crown of the road. So this is in the fall. The vegetation is pretty well matted down. Fairly sparse vegetation for most of this. So contours appear to reflect the terrain surface, just visual exploration. They look very, very good. So they're crossing this hillside, a very smooth, uniform slope. Some of the steeper cut slopes, the contours are parallel. It's a nice uniform slope. So the surface model appears to be very good. Do have some issues with some of the streams. Don't have a break line on the streams. However, the contours look pretty good. I would suggest that if you really want an accurate um, contour of the area where the stream crosses, that you might want to actually do a break line on the ground and then import it and use it to control the contours. So the drone imagery appears to be very useful in areas of fairly low vegetation, does even a better job of removing it. So drone does appear to be a very useful tool in our geospatial toolbox. Just speaking with one of our alumni who has been using drones with the firm that they are with, and they're at the point where they're going to just a drone that takes good quality vertical imagery and just put it in their survey crew vehicle that they can pull out and use uh, if it's needed. Well, that concludes my presentation. Hopefully you've found something of use and value here. If you're just getting into a drone usage or considering it, maybe this information will help you with that decision. Thank you for your time.